titled Determinants Sheet 1. Now the first problem of the sheet is about being able to express this as a product of two determinants, This thing could be written as, now there is no cardinal rule on how you would express a determinant as a product of two determinants. It has to be done only by inspection. Right? So the more you practice, the better you get on learning how to express a determinant as a product of two determinants as and when required. Now, this is like tan A, cot A, 1. You try and match one or two terms. Chances are that it's going to match. If it doesn't match, that means, maybe the whole idea of expressing it as a product of two determinants might be just futile. Now, tan A, cot A. Look at the first term. Look at the first term, which is 2. Now, 2, one of the ways you could have obtained 2 is if this was like cot A, tan A, and 0. Then the first term would have been like tan A, cot A, plus cot A, tan A, plus 0, 0, which is going to be 2. Right? Now, look at the second term, which is again revolving around tan A, cot A, and 0. The first row will remain intact. Now it's about the second row. Now, the second row, again, look at the second term, which involves the first row of this and the second row of this, right? So, tan A and cot A are all right, are existent. Now, what we need is cot B and tan B. Cot B and tan B. See? For the second term, we need cot B, tan B. See if it matches. The second term now would have been tan A, cot B, plus cot A, tan B, plus 0, 0, which matches with the second term? Yes or no? Do you realize that? Similarly, look at the third term. Tan A and cot A are intact. What we need is cot C and tan C. So, put a cot C and tan C, 0. And then, of course, tan A, cot A, tan B, cot B, tan C, cot C. Yes or no? That will match. So you will have to gauge the determinant for one or two terms and try and, generalize matters here and see if it works for all terms. Right? Very clearly, this determinant is 0. This determinant is 0. So the product is going to be 0. Yes or no? Do you realize that? I hope all of you know how to multiply two determinants. Right? You could do row by row, column by column, row by column, column by row. All possible things are allowed because a determinant could be transposed. Rows could be converted into columns or columns could be converted into rows. Right? Transposition will not alter the value of the determinant. So multiplying by row or multiplying by column or column by row or row by column will tantamount to the same thing. Right? So do you all understand what I did here? And this was inspection. It might not always work. Right? You have to examine a few terms and see if you can extract the right rows and columns out of the terms that are prevalent. Got me? All right, let's look at the next one. And this would come out of practice. The second problem is a determinant which is cos A, sin A, cos A plus D, This is fairly simple because I could have expanded this cos A cos D minus sin A sin D, etc. Right? This is cos B cos D minus sin B sin D. And then you can break it up into two determinants, right? One determinant is going to be cos A sin A cos A cos D, cos B sin B cos B cos D, minus cos A sin A sin A sin D cos B sin B sin B sin D cos C sin C sin C sin D. Right? Obviously, you can take cos D common from this. If you took cos D common from this determinant, from the third column, and sin D common from the third column of this determinant, this is what happens. The first and the third column become identical here, and in this case the second and the third column become identical. So both determinants are 0. The value of this determinant would be 0. Yes or no? Hey, number 3, just to avoid clutter, see, I take A as beta plus gamma minus alpha minus delta whole squared as A, right? This whole squared as B, A, then B as gamma plus alpha minus beta minus delta whole squared as B, and C as alpha plus beta minus gamma minus delta whole squared as C, right? Then the required determinant evidently has the form A squared B squared C squared A B C Yes or no? Right? Now from the determinant that I just discussed, this is going to be interchanging these two, right? Is going to be minus of A minus B into B minus C into C minus A. I hope you realize why the minus sign, because the original one had this column here and this column here. Got me? So all that you need to do is plug in A minus B, B minus C, C minus A from those, and there you get the value. Huh? If we? Then also, it does not matter. Any two columns you interchange, the sign will become negative. It does not matter which two columns you change. If you are interchanging an even number of times, the sign will be retained. If you are changing an odd number of times, the sign will change. All right. Simple, right? Now it's given A28, a 3-digit number A28, 3b9 and 62c are 3-digit numbers. A, B, C are integers between 0 and 9 that are divisible by a fixed number k. So these 3 numbers are divisible by k, rk. We want to show that this determinant delta, which is A3689C 2b2, we want to show that this is also divisible by k. Given that these are all divisible by k, we want to show that this is also divisible by k. Now, see, for example, to obtain A28, to row 2, I add 100 times row 1, that will give me 100A, and 10 times row 3. Then I'll get a A28. Yes or no? Same with other entities. So the operation I perform is the operation on R2. What's the operation that I perform on R2? R2 to be replaced by R2 plus 100 times R1 plus 10 times R3. This is what I do. 100 times R1 means 100A plus 20 plus 8 would give me 828. Yes or no? A28, similarly 3b9 and 62c. Obviously, the second row is divisible by k. So you could have taken k common and the determinant would be divisible by k. Yes or no? Right? Clear? Alpha, beta are the roots of this quadratic. Ax squared plus bx plus c equal to 0. And we define Sn as alpha to power n plus beta to power n is how Sn is defined, n greater than or equal to 1. We want to find the value of the determinant. We want to find the value of this determinant. Clear? Very clearly, S1 would be 1 alpha plus beta, S2 would be alpha squared plus beta squared, etc. In the first place, let's do that. First row. Second row. Now, a guess that I would want to make to begin with is that, I can see that it's a symmetric determinant. Aij is the same as Agi. See, you convert rows into columns and columns into rows, the determinant will remain the same. Perhaps, and it may not always happen, since it's a symmetric determinant, it might be square of another determinant. Square of any determinant, that means when you multiply a determinant with itself, it's always going to give you a symmetric determinant. Those of you who've not known this fact might want to quickly take a look at my video. I have uploaded on the LAN here on determinants, and you would get to know some of these things. So I'm guessing that this is expressible as the square of a determinant. That means product of two identical determinants. Product of two identical determinants. I'm guessing. Right? Now, since again, I'm venturing into a territory where I want to express this as product of two determinants, I will have to, take chances, in the sense that I would have to make guesses, reasonable guesses, and see if it takes me to the destination, right? Now, since it's about attempting to express this given determinant as product of two identical determinants, there is a 3 that I see here. Now this 3 is like 1, 1, 1 and 1, 1, 1. 2 rows, 1 each, will give me 1 into 1 plus 1 into 1 plus 1 into 1, which is going to give me a 3. Let me explore that. So the first row I populate with ones with an attempt to get a 3 here. Now the second one is 1 plus alpha plus beta. So what I try and do is this with the second row of this is likely to give me 1 plus alpha plus beta. So 1 into 1 with this, then 1 into what will give me alpha? Alpha. 1 into what will give me beta? Beta. Right? Similarly, 1 plus alpha squared plus beta squared. So 1, 1, 1, 1 with alpha squared and beta squared would give me the third term. So I've been able to express this. And now make this identical to this and see if the terms match. So because I'm trying to express this as product of two identical determinants. One I've obtained, the other one, since I'm guessing that it's going to be identical, 1 alpha squared beta squared. Check this out. Does it match? It does. It does. It does, right? Now, again, like the previous determinant, this is a standard 1, 1, 1, 1, 1, 1, A, B, C, A square, B square, C square, itself that form. 1, 1, 1, A, B, C, A square, B square, C square is A minus B into B minus C into C minus A. That's the form. That means, this determinant 1, 1, 1, 1 alpha beta, 1 alpha squared beta squared is going to be A minus B, which is 1 minus alpha, into B minus C into C minus A. Right? Yes or no? I need to find the value of this then, and then square it because they are identical, right? This with this. So this is like alpha minus 1 into beta minus 1 into beta minus alpha, which is like alpha beta plus 1 minus alpha plus beta into beta minus alpha. Now the value of this alpha beta, the product is C by A minus sum of the roots minus B by A into beta minus alpha. Yeah. Minus, so plus B by A, right? Yeah. Minus of alpha plus beta, which is B by A. Clear? So I need to square this to get the required determinant. So the required determinant is going to be A plus B. This is A plus B plus C divided by A whole squared into beta minus alpha whole squared. That's what this is, right? Square of this, which is A plus B plus C by A, right? This is A plus B plus C by A square, and this is alpha plus beta whole squared minus 4 alpha beta. right? And alpha plus beta whole squared would be b squared by 4a squared, b squared by a squared, and this would be 4c by a. You can plug in, right? Alpha plus beta you can plug in as minus b by a, so this would become b squared by a squared, this would become 4c by a, etc. Clear? Hmm? Yeah. Oh, that's fine. But you get this right? So you know this determinant will never leave you. 1 1 1 a b c a square b square c squared is a minus b into b minus c into c minus a. You must remember, right? Similarly, you know this determinant 1 1 1 a b c a square b square a cube b cube c cubed. This will be a determinant of degree 4. Degree 4. And it will have the same factors a minus b, b minus c, c minus a. But then, you know, it's going to be symmetric about a, b. It needs another degree here. So it needs a linear expression in ABC here, right? So that would turn out to be, on equating coefficients, will turn out to be a plus b plus c into k. And then by equating the coefficients of the leading term bc cubed, you can get k equal to 1 is what you'll get. So this is another determinant whose value you must remember. This is another standard determinant. You must remember this. A minus b, b minus c, c minus a plus b plus c. Want to remember this. Okay? Is there a problem? No? Yes, I will. Can I remove the clutter and then explain? Just remove the rest of the and explain why this determinant should be equal to this. See, one thing very easy to see, that when you expand this determinant, it's going to be a homogeneous expression. Every term of that expression would be of degree 4. See, bc cubed, b cube c, ab cubed, a squared b, a cube b, etc. Every term would be of degree 4, right? And plugging in a equal to b, b equal to c, and c equal to a, the determinant vanishes. Therefore, a minus b, b minus c, c minus a must be inherent factors. Now, but these three will make it only degree 4. It will be homogeneous but of degree 3. But I need another degree in it. That means with the product, I need another linear expression in a, b, and c. I need another linear expression in a, b, and c, which should not exhibit any bias towards ABC. And a linear in ABC which does not exhibit any bias towards ABC would be KA plus KB plus KC, K coming out. So K times A plus B plus C. And K is 1. That could be obtained by equating the coefficient of BC cubed on the left hand side with the coefficient of BC cubed on the right hand side. You would get K equal to 1. Right? In fact, this is another standard determinant. This is degree 5. It's going to be a homogeneous expression of degree 5, as you can see. This will produce 3 degrees here. You need 2 more degrees, and that would be obtained out of AB plus BC plus CA. Another one that you want to remember. सोचना. This is also degree 5. And this is going to be remember some of these. Okay. Are you all familiar with the cyclic determinant? Cyclic determinant is one like this. ABC, BCA, CAB is a cyclic determinant. And again, this is a standard determinant you can obtain by adding R1 plus R2 plus R3 to R1, right? To R1 add R2 and R3. You can take A plus B plus C common. You would find the value of this as minus of A cube plus B cube plus C cube minus 3ABC, which is the same as minus of A plus B plus C into A square plus B square plus C square minus AB minus BC minus CA. This determinant also you want to remember. All of this you can very easily prove. These are very ordinary things, very easy to prove, but it's best to even remember these results, some of these results. Okay. 6, part 1. Again, you know, the idea is to be able to express this as product of two determinants. Look at the first column, for example. It's the inner product. The first column is the inner product of A1, B1, 0. First column. First term, alpha 1, beta 1, 0. Do you realize that? That's the first term. It's the inner product of these, A1, alpha 1, B1, beta 1, 0, 0, right? The second term of the first column, I mean, you could transpose, right? The first column could have been made the first row also, right? Look at the second one. That's the inner product of A1, B1, 0, alpha 2, beta 2, 0. That's the second term of the first column, right? Look at the third one. The third term of the first column is like A1, B1, 0, inner product of alpha 3, beta 3, 0. Do you realize that? Yes or no? Yes or no? Right? I mean, the first column, imagine that to be the first row. Then these inner products will work. And therefore, the given determinant, you would expect the following at least. A1, B1, 0. Then first row of the second determinant, second row of the second determinant, third row of the third determinant. To get these numbers, you would have alpha 1, beta 1, 0. And then extrapolate. Right? Which will be 0. I mean, what you could do is the given determinant, so that you have a row by row multiplication at your disposal, transpose the given determinant. Make the first, imagine the first column to be the first row, second column to be the second row, third column to be the third row. Then a row by row multiplication of these two determinants will give you the required determinant. Yes or no? You know what I'm saying? The given determinant, transpose it, convert the rows into columns and columns into rows. Then a row by row multiplication of these two determinants will give you the given determinant transposed. The given determinant transposed. You know what I'm saying? This then will turn out to be 0, expanding about the third column. Clear? All right. Again, a squared minus 2a and then 1. I'm trying to isolate a and x. Terms that contain a and terms that contain x, I'm trying to isolate. Okay, now this, so I'm just testing waters with one term. So a squared, I should have a 1 here, so that a squared into 1 is a squared. Then minus 2ax. So I would expect this to be x. And then x squared. So I would expect this to be 1 into x squared, this. Yes or no? You know what I'm saying? Then this with this would give me a minus x whole squared. Yes or no? This row with this row would give me a minus x whole squared, which would be this term, right? And similarly, what I have for a, and then, you know, this is a minus y whole squared. So this should be like 1y squared. Yes or no? Then this with this would give me a minus y whole squared. And then a minus z whole squared. So this should be like 1z squared. So that this inner product with this inner product would give me a minus z whole squared. Now whatever I have for the first row in a, for the second row I should have in terms of b squared minus 2b, 1, c squared minus 2c, 1. Yes or no? Got me? Clear? Obviously, I can take minus 2 common from this. And take recourse to this standard determinant. Let me tell you the standard determinant. This determinant is a standard determinant. Its value is a minus b into b minus c into c minus a. How many of you know this as a regular determinant? Okay, good. So those of you who don't have recollection of this as a regular determinant might want to take cognizance of this. Now, again, it's not a difficult proposition to see why this would be true. Because, see, if you plug in a equal to b, the first and the second column become identical. So a minus b must have been a factor of this, right? If you plug in b equal to c, the second and the third column become identical. So you would expect b minus c to be a factor of this. And if you plug in c equal to a, the first and the third column become identical, the determinant would vanish. So c minus a must be a factor. And this must be some k times this. This must be k times this. Now why k? Because this is degree 3, bc squared, b squared, c, etc. All would be degree 3. So k should be degree 0. K should be a pure number. Now, how does one obtain this pure number? So this equal to this is an identity. Look at the leading term of this determinant, 1bc squared. So coefficient of 1bc squared in the determinant is 1. Coefficient of 1bc squared on the right hand side must also be 1. K therefore would have to be 1. So that coefficient of 1bc squared is 1 on the right hand side also, causing this to be equal to this. Yes or no? You know what I'm saying? Right? Do you all realize? So remember this. Remember this as a regular determinant. And see, if you convert rows into columns and columns into rows, what will happen? It will remain the same. So for example, I convert the first row into first column, second row into second column, third row into third column. Then this determinant will remain the same. Yes or no? Right? Now, see, this then is the same as this. 1a, a squared, 1b, b squared, 1c, c squared. So the value of this is going to be what? X minus y into y minus z into z minus x, the second determinant. Yes or no? Because this is the same as this. Look at the formation. Instead of x and y, you have AB. X, y, and z, you have A, B, and C. Same thing, right? Now look at this. See, I could have transposed this here, and I could have transposed this there. What would happen? If I interchange these two, what would happen? The sign of the determinant would change, right? This is how obtained. So this would be A minus B into B minus C into C minus A, but with a minus sign, because this can be obtained from this by interchanging the first and the third column of this, right? So then this would be a minus would emerge, causing this to be plus. So this is going to be twice A minus B into B minus C into C minus A. That's the value of this determinant. Are you all fine with this? Can I wipe this off? Seven. N is a positive integer, fixed positive integer. Right? We want to show d divided by n factorial whole cubed. Minus 4 is divisible by n. Minus 4 is divisible by n. That's what we want to be able to show here. Clear? Now, first of all, let me somehow obtain d by n factorial cubed. I could have taken n factorial common from the first, second, and third rows, giving me a n factorial cube in the very first place. You know what I'm saying? Take n factorial common from the first, second, and third rows right away. So when you do that, you get a n factorial cube wriggling out, right? Then this would be 1, n plus 1, n plus 2 into n plus 1. This would be n plus 1, n plus 2 into n plus 1, n plus 3 into n plus 2 into n plus 1. This is going to be n plus 2 into n plus 1, n plus 3 into n plus 2 into n plus 1, n plus 4 into n plus 3 into n plus 2 into n plus 1. This is what transpires, right? Yes or no? You know, realize what I've done here? Okay. Now, let's see if there is further simplification in the offing before I venture into some conclusions. From this second column, I could have taken n plus 1 out from the second column. From the second column, right, n plus 1 could have been taken common. From the third column, n plus 1 into n plus 2 could have been taken common. Yes or no? From the second column, n plus 1 could have been taken common. From the third column, n plus 1 into n plus 2 can be taken common. Therefore, what I do is, so right here, let me do that, right? The problem with determinants is that it consumes a lot of space. So you have to kind of maintain some austerity. So n plus 1 whole squared into n plus 2, right? So n plus 1 taken common will leave me with 1 here. N plus 1 taken common, n plus 1 taken common from this. Now n plus 1 into n plus 2 taken common from the second will give me 1 here, will give me n plus 3 here, and will give me n plus 3 into n plus 4 here. Yes or no? Right now? Clear? Now again, I want to expand about the first row, but let me economize further. What would I do? C2 minus C1 and C3 minus C1 so that these elements become 0, right? So I perform these two. On C2 I do a C2 minus C1. On C3 I do a C3 minus C1 so that for the first row the second and the third entries will become 0, right? So this minus this 0, n plus 2 minus n plus 1, which is n plus 1. N plus 2 if I take common from this, then n plus 3 minus n plus 1 will give me 2, right? So this will be twice n plus 2. If I happen to make a mistake, please fix me. Do you realize this is twice n plus 2? Right? Okay, so this minus this again 0. N plus 3 minus n plus 1, which is 2. And then this minus this. Which one? This one. This one 1. This is all right, right? Then this, what was the entry here? 1. So 1 minus 1. What was the entry here? N plus 3 minus n plus 1, that is 2. And this is the entry here, n plus 3 into n plus 4. So nothing common, huh? N plus 3 into n plus 4 minus n plus 2 into n plus 1. Is it right? Was this the entry here? Was this the entry here originally? Then this minus this. This is n squared plus 7n plus 12 minus n squared plus 3n plus 2. Right? N squared would get cancelled. So 4n plus 10. Isn't it? Isn't it? So this would be 4n plus 10. Right? This is what you get. Now you expand about the first row, and this D by n factorial cubed is what you need to deal with, right? And this into this minus this into this, if you expand about this, I'm only assuming that, in the process of erasing and writing, I have not made a computational error. If I have, fix it. I'm just assuming because I erased and then I, manipulated, so it might have goofed up, but you want to check this. N plus 1 whole square, and then 4n plus 10 minus 4 into n plus 2. Yes or no? Right? So far so good, right? So 4 and 4n will get cancelled. 10 minus 8, 2. Right? That will be the value of this determinant, expanding about the first row. So 2. Right? Now I want to do a d by n factorial whole cube minus 4. So what I do is, see, the minus 4 can come out of this. 2 into 2 into 1 will give me a 4, which can go on the left hand side. Right? And that will be the only term not containing n. Everything else will contain n. Yes or no? See, if I multiply this out, then the only term not containing n, independent of n, would be what? 2 into 2, 4 into 1. Now, which I transpose on the left hand side, that means if I took a d by n factorial cubed, and the only term that does not contain n is 4 here, if I put on the left hand side, the rest of the terms will have powers of n and powers of n. So the rest would be divisible by n, yes or no? Clear? Do you realize that? So you don't have to do a further calculation. You can just transpose 4 on the left hand side, and rest, of course, the term independent of n here is 4. Everything else contains n on the right hand side, which I have transposed and gotten ridden off. Clear? Number 8, you know, this is a standard determinant. Equal to this is a standard determinant. You want to remember this, but let's see how to prove this. So obviously, you know, if I start with this delta, this left hand side determinant, I could have taken A common from here, B common from here, and C common from here. Somehow force a ABC outside the determinant. And then we'll manipulate. Because I know for sure, you know, I'm doing a little bit of a cheating. Because I know that there is an ABC that I need, so I know I force it out. So let's force the ABC out of the cocoon. A from the first row, B from the second row, and C from the third. I get 1 plus 1 by A plus 1, 1 by A, 1 by A, 1 by B plus 1, 1 by B. This is what I get. 1 by B. Okay, now to row 1, if you add row 2 and row 3, you get this number, right? So another level of cheating. So row 1, I do a row 1 plus row 2 plus row 3. This is what I do, right? Sorry to get a little microscopic there for want of space, right? So 1 by A plus 1 by B plus 1 by C plus 1, 1 by A plus 1 by B plus 1 by C plus 1, 1 by A plus 1 by B plus 1 by C plus 1. That's the first row after doing that operation, right? And then 1 by B plus 1, 1 by B. And obviously, this helps me take this entity out. This is what we do. Then obviously, you know, you want to do row 2 minus row 1 and row 3, C2 minus C1 and C3 minus C1, right? We do these two operations. On C2, I do a C2 minus C1. On C3, I do a C3 minus C1 so as to make these 0, right? So C2 minus C1, this will become 0. This will become 1. This will become 0, right? And then on C3, C3 minus C1, so 1 minus 1, this is 0. This is 0. And this is 1. Expand about the first row. So that's going to give you just 1, right? That's number 8. And from now on, remember this as a regular result. Remember this as a regular result. Okay? Of course, you know, all these regular results that I'm talking of, you don't use these as regular results in your board exams. It'll make you irregular. Don't do that. Huh? These are regular results for the consumption of our class and for your competitive exams. But for the sake of your board exams, nothing is regular. All right? Go using the regular row column manipulation for every standard thing that you see and obtain that. Right? So don't take chances, no hanky panky. All right? So not a regular result for any exam. I mean, imagine the tragedy of the subject. What has it come to? You know, when I am coming to teach you mathematics here, I feel so guilty, you know, polarizing the subject like this for you, saying, hey, this is a regular result for this exam and not a regular result for that exam. How tragic it is when a teacher comes up to you and, you know, he says all this. This is so bad. I mean, it is mathematics. What regular, what not regular. You know, for this exam regular, for that exam not regular. But, pardon me, you know, you're at the brink of 2 major exams. So, you know, I'm almost, the system has forced me to, you know, draw you into this polarization. I would hate to do this ever. But let's accept some bitter truths with resignation. Shall we proceed? क्या ओ हम बोले क्या झाड़ दी ना oh come on don't take my cheating here with a pinch of salt I will enjoy, you know, forever remember the love-hate relationship you guys enjoy with each other. No, I will not get into further description of the love and the hatred. But, you know, because that can get very bizarre. And, you know, if I cross a certain boundary, it might also start looking ugly. Huh? No. Whole cube, क्या? Cube ही होना चाहिए because this into this into this is degree 3, so it couldn't have been a square anyways. So see, column 1, column 2 plus column 3. See? This will become A plus B plus C, yes or no? This will become A plus B plus C. This will become A plus B plus C is what this would become, right? So this determinant on performing this operation, the first column will become A plus B plus C. Oh, shall I just write it here? Because otherwise I won't have space on top. All right? And then, of course, I can take A plus B plus C common from this. Now, what I could do is, I want to expand about the first column. I want to make this 0 and this 0. So I'll perform the following operations. On row 2, I'll do a row 2 minus row 1, right? On row 3, I'll do a row 3 minus row 1. Is that acceptable? Right? So this minus this, 0. This will become minus of A plus B plus C. This minus this will become 0, right? Row 2 minus row 1. And row 3 minus row 1. So this is going to become 0. This is going to become 0. This will become minus of A plus B plus C. Yes or no? Expand about the first column. So 1 into minus a plus b plus c into minus a plus b plus c, 0, 0. So that gives me a plus b plus c sitting out, and a plus b plus c whole squared coming from here. So a plus b plus c whole cube. Yes or no? We want to show without expanding at any stage that this is 0. Without expanding at any stage, we want to show that this is 0. Now this could be written as sum of two determinants, 1a squared right? I'm not allowed to expand. I'm not allowed to expand, right? So either I want to convert this to this or this to this and show that they are identical. Suppose this determinant I call as delta 1, then what is my delta 1 equal to? I want to show that delta 1 is equal to this delta, right? So delta 1 is 1a bc Now see how I want to do is, I want to create a square and a squared and a is what I want to create in the first line. So I multiply the first row by a so that I can get a squared and a. Two terms will match. I want to multiply the second row by b. I want to multiply the third row by c. So when I do that, and therefore, you know, if I multiplied by abc, I'm obliged to divide by ABC, maintaining the status, and then I want to take ABC common from this, the third column. So if I took ABC common from the third column, that will cancel off with this ABC. This will then be rendered a squared 1, b squared 1, c squared 1. Now, to reduce this to this, what are the two operations? I'll interchange the first and the third columns, right? And then I interchange, after having done that, I interchange these two. Then I will get that, yes or no? So first time I interchange, it becomes minus. Second time I interchange, it will become plus. So then this will be equal to this, and the determinant will be equal to 0, yes or no? You know, there is a mistake here. This make it 11. Hey, NCR plus NCR minus 1 is N plus 1 CR, right? So NCR plus NCR minus 1 would give me 11C5. NCR plus NCR minus 1, 11C7 plus 11C6 is going to give me 12C7. NCR plus NCR minus 1 would give me 13C9. So which means I do the following. On column 2, I do a column 2 plus column 1 is what I do. Right? So this will become 11C5. NCR plus NCR minus 1 would be 12C7. NCR plus NCR minus 1 would be N plus 1, that is 12CR, right? So this will become 12C7. NCR plus NCR minus 1 will give me 13C9. Then, very clearly, if this has to be 0, then for m equal to 5, this column and this column will become identical for m equal to 5. See, m equal to 5, m equal to 5, this is 7, m equal to 5, this will be 9. So, very clearly by observation, m must be equal to 5. Good question. M equal to 5 for sure is one of the values. We will certainly have to inspect more to prove that that's the only value. We will have to perform more operations. To be honest, m equal to 5 is one of the values that I can speak of at the very onset. It is, although I can say it probably is the only value. It's not just the only value observed, because to be able to match with 11, 12 and 13 with 3 of these for the same for different values of m could be very unlikely. But I will not comment it right ahead and say that that's the only value. That's one of the values which I can see by inspection. We will have to explore more, but probably it is the only value. I can say probably it's the only value. I mean, I would actually have to think more to uniquely establish that that's the only value.